Up until now, we've been explaining the structure of molecules in terms of Lewis theory, Lewis structures. And it's a pretty successful and very simple theory. But there are some things that don't quite make sense. There are some questions that we can't quite answer with Lewis theory. For one thing, why do we have lone pairs? Why don't we have lone triples? Why do we have bonding pairs? Why not one electron for a bond? Why not three? What's so magic about the number 2? Lewis theory can't really answer that. Now, you might remember that when we talked about filling up orbital diagrams, that 2 electrons could fit in an orbital. And it turns out that if we bring orbitals back into the picture, we can explain why Lewis structures are built the way that they are on a much more satisfying and deeper level. That's the idea behind valence bond theory. Let's look at how this works, starting with the simplest possible molecule, H2. Let's draw a Lewis structure for H2. Here's the skeleton structure. How many electrons do I have? There's 1 valence electron in each hydrogen, so I have a total of 2. And then I connect the structure, and I've used up my 2. I'm done. So there's the Lewis picture of the H2 molecule. And it makes sense. We can kind of see why that bond holds together the 2 atoms. Here's one of the positively charged nuclei of the hydrogen. And here's another positively charged nucleus for that other hydrogen. And then the bond is an electron pair, so it is 2 little negatively charged electrons in there. And what's happening here is that the nucleus is attracted to that negative charge, and this nucleus is attracted to the negative charge as well. And that holds the molecule together. That's why that stick is actually a bond that holds the 2 hydrogens together. But what happens if we bring the orbitals back in? Instead of looking at just the count of the valence electrons, let's draw the orbitals that we have in here. Here is the nucleus for one of the hydrogens, and here's a 1s orbital for it. And here is the other hydrogen. I'll draw it in red. Not a very good circle. And here's a 1s. Should be a circle. And there's its nucleus. When I push the 2 orbitals together, they overlap here. And there's a buildup of negative charge wherever the orbital overlaps with another. Remember, you can think of the orbital as sort of a charge cloud, a negative charge cloud. We say sometimes the electron is in an orbital, but really what we mean, the electron is the orbital. The electron is the negatively charged cloud here. And when these 2 clouds overlap, there'll be a thicker cloud there. This overlap region between 2 half-filled orbitals is going to produce a buildup of negative charge between the 2 nuclei and hold the molecule together. It's called a valence bond. So that's where this theory takes its name. We look for overlaps between 2 half-filled orbitals. Now I'm saying an overlap between 2 half-filled orbitals, but really there's a further restriction. One of them has to be a spin-up electron, and the other one has to be a spin-down. So you not only have to overlap 2 half-filled orbitals, but they have to have opposite spins. Now there's another way we can draw the valence bond structure here. We can do it with energy level diagrams. Here's the energy level diagram for a hydrogen. Its ground state has the electron in a 1s orbital. Here is the 1s orbital for the other hydrogen. Now, this one has got, say, a spin up, and this one has got a spin down. I can draw the valence bond as an overlap, a tie, between the spin up on one, a half-filled orbital with a spin up, and a half-filled orbital with a spin down. That line that I just drew is the valence bond. So we can draw it like this in terms of the shapes of the orbitals, or we can draw a valence bond like this in terms of the energy level diagram. Let's try another valence bond. Let's do the HF molecule. Let's do a Lewis structure for it first. There's H and there's F. I have 1 electron from the H and 7 valence electrons from the F from the periodic table. So I have a total of 8 valence electrons to work with. I connect the structure. That took away 2. I have 6 left. I dump them all on that atom, and now I'm done. And everything here is satisfied. Remember, hydrogen is satisfied with a helium configuration, so it only needs the 2 that are in the bond here. And this has got an octet. So I got a bond and 3 lone pairs. Let's do this same picture in the valence bond theory. Let's do an energy level diagram for the hydrogen. And let's say the hydrogen has, it doesn't matter whether we say spin up or spin down, as long as it's the opposite of what it's going to be in the other atom. So let's do the energy level diagram for the fluorine. Fluorine's configuration was 1s2, if I look at the periodic table, 2s2, 2p5. So let's draw an energy level diagram for it. 1s, 2s, and then we have 3 2p orbitals. So they all have the same energy, so they're all at the same level. So this is what the energy level diagram looks like for fluorine. Now let's fill it in according to the electron configuration. There's 2 electrons in the 1s. There's 2 electrons in the 2s. So this is just an orbital diagram that I'm doing here. And then there's 5 in the 2p. 1, 2, 3, 4, 5. I put a spin up and a spin down whenever I had to start pairing them up. So now I'm going to overlap the half-filled orbital on the H with the half-filled orbital on the F, and that's the valence bond there that I just drew in. Now it looks like it's going to be an overlap between a 2p orbital and a 1s orbital. Let's draw that. Here's the hydrogen 1s orbital. And let's draw just the fluorine 2p orbital. Let's see, let me do it in a different color. And here's the fluorine nucleus, that little red dot that I have here. Let's see, let me move this up a little bit. And there's the overlap. That is the valence bond. Now, what about the other orbitals? You could draw those in. And it would show you that you had a lone pair in a 2p orbital going up and down like this, and a lone pair in a 2p orbital going in and out of the paper like that. We're going to look at more complicated structures like that in the next video. But that's the basic idea behind valence bond theory. You form a bond as an overlap between 2 half-filled orbitals.